Now, why do we need small numbers? Why is that helpful? The reason for that is we can take small numbers and we can try to pack them into a more efficient representation. We can try to use fewer bytes to represent these smaller numbers. So here's this very simple example of this. This is called V-byte encoding. The basic idea there is you are going to use variable number of bytes depending on how big the number is that you're trying to encode. So if your number is anywhere between 0 and 127, we're going to use 1 byte to encode it. If it's between 128 and, what is it, 16,000 something, then we're going to use 2 bytes, and so on and so forth. So what is the encoding itself going to be? Instead of using 8 bits in a byte, you're going to use the 7 bits to represent the number itself, and the first bit, the high bit, is going to have a special purpose. It's going to have a special function. That bit will tell us if this byte is the last byte of an encoding. Right? So if I have the number 6 and I want to encode it, this is what the encoding would look like, right? So if you ignore this 1 for a moment, this is the binary encoding of 6 itself, right? So this bit corresponds to 2, this bit corresponds to 4, 4 plus 2 is 6. So this encodes the 6. And the fact that I have a 1 in the high bit, this means that this is the last byte that represents an encoding for this number. So same for byte 127, right? The 7 ones, that's the binary representation for 127, and this tells me that this is the last byte of an encoding. Now, if I have 128, which is 1 bigger than that, you can no longer represent that with 1 byte. So now what would happen if this was a normal number? If this was a normal number, I added 1 to this, all of these 1s turn into 0, and the 8th bit, the high bit, would turn into 1, right? That's how things work. In this case, you do exactly the same thing, only this 1 doesn't go into the high bit, because the high bit is special. It goes into your next byte. Okay? So all of the numbers, all of the 1, 2, 3, 6, 7 1s from here are zeroed out, and I get a 1 in the next position. Only now the next position is in the next byte, right? And this byte doesn't have any other ones, and the high bit of that byte is 0. What does that mean? This means this is not the last byte of the representation. So when I'm looking at this string, I know that this is the first byte of a multi-byte encoding, so I need to look further. So I look at that, and then I look at the next number, and then I realize, okay, this is the last one. Right? So the way you decode one of these things is you first identify the boundaries of numbers by looking at the high bits, and then once you've bracketed the numbers themselves, you throw away the high bits and read off the remaining representation for the number. Okay, so let's go through an example. I have some numbers encoded in this string right there. Right? So our goal is to deconstruct it. Our goal is to uncompress this. Right? So now the first thing is 1. What does this mean? Yeah. So this is this byte. So the byte ends right there. Right. So that's 1, 2, 3, 4, 5, 6, 7. So the byte ends right there. So this is the last byte, and because it's the first one, it's the last and only byte. So what I know is this is a number that consists of 1 byte, exactly. Right? So what number is it? It's number 1. Right? Now the next one, I have a 0. What does this mean? It's a long number, right? It's more than 1 byte. So let's see, 1, 2, 3, 4, 1, 2, 3, 4. Okay. And then this is the next high bit. And the fact that I have a 1 here tells me what?
That's 16-bit.
Yes, yes. So the next number is going to be a 16-bit number, right? And it's going to have 1, 2, 3, 4, 1, 2, 3, 4. It's going to have a 1 here, right?
120.
And then that where it ends? Yeah. So what's the value? Okay. So it's 130, right? So the byte, the number ends right there. These are special, so you throw them away. This one corresponds to 128, and then this would be a 1, but this is a 2, right? So 128 plus 2 is 130. So that's how you do this. And then the last one is just a 2, because it's a 1 byte number, okay? So what this allows you to do is this allows you to pack different numbers into different numbers of bytes. Why do I need to do this? Why can't I just use one byte for everything? I'm sorry?
For the sparse indexes?
For the sparse indices. Why?
Because they have big deltas.
Yes. So in the sparse indices, you will have big deltas between the numbers. So the word could occur in document 1, and the next occurrence could be in document 1 billion. So the delta is going to be 1 billion. And there is no way I can squeeze 1 billion into 1 byte. I could squeeze 1 billion into 4 bytes. So I could maybe represent every delta with 4 bytes. Why shouldn't I do that?
There's no reason to use small number of deltas.
Yes. So if I did that, I would be wasting a lot of valuable space, right? Because most deltas are small. It's just that sometimes they're big, and I don't want to throw them away just because they're big. That would defeat the purpose of the data storage. So you want to keep both the small numbers and the big numbers, and you want to spend as few bits as you can on the small numbers, because they make up the bulk of your index. And then when you get a big number, yeah, you take a hit and you represent it with multiple bytes. So this is a data structure that allows you to, to pack lots of small numbers into small bit counts, and then use bigger numbers for the big deltas. Right. So now this is probably the simplest way to do variable byte encoding. So this is V-byte. There are many other techniques which are a lot more sophisticated than this. So if you're interested, look up Elias gamma codes. So there you're actually packing things inside a single byte. So you could use so here a byte is the smallest unit that you have. And with Elias codes you can actually use you can pack multiple numbers inside the same byte, giving even more compression. The big downside is if you go that route, you actually have to do bit-level operations, and byte-level operations are a lot faster in almost all assembly languages. So if you start doing bit masking, everything becomes a lot slower. So this is a compromise. It provides a good amount of compression, and it's also really, really fast. By the way, I guess complexity-wise, these techniques, compared to normal compression, compared to Lempo-Ziv, for example, they're very, very naive, and they're also very, very fast, because you can process things in one go. You basically just walk down the list, you bracket the numbers, convert them to decimal values, and you add subsequent numbers to each other to undo the delta compression. And you can reconstruct your list basically in one go, and you don't need a lookup table or anything for this. So very fast technique. All right.